Okay, so unit 9, it's going to start with the Gibbs free energy thermodynamic review. I highly recommend you just listen. You've gotten most of this either through physics or through unit 7 content, the end of unit 7. I'll introduce a couple new equations. And then what's going to happen is this unit's going to really connect Gibbs free energy with redox reactions and tracking electron movement in reactions. And this is where electrochemical cells and physics people tend to thrive. This is where I die. Okay, so here's my little pre-claimer statement. I say it every year. Don't ask me too many questions. I'm honestly, this is the subject. This is like that particular chapter that I learned just what I have to learn to teach you. Like I have no personal interest in this. I know how to do redox reactions, half reactions. If you ask me how to build an electrical chemist cell, I'm like, read the directions, man. Look at the picture. Okay. So that's where I'm at. So I'm just going to preface that and let's go for this. So, we learned in unit 7 that one Gibbs free energy is basically a non-real energy that we use that relates enthalpy and entropy to predict the spontaneity or the natural occurrence, the favorability of a reaction in the universe. So the Gibbs free energy that we learned about was known as Gibbs-Helmholtz equation, which is G is equal to change in H for the reaction minus the temperature times the change in Kelvin. This is always in Kelvin. Times the change in entropy. And we tend to also, by the way, measure this under standard state conditions so that we get a tabularized data for every variable, barring temperature. Okay. So we know that at standard conditions, we have constant temp and pressure. So don't forget at standard conditions what that really means. Okay. What we have is a constant temp and pressure where the temp is 25 degrees Celsius and pressure is 1 atm. All right. Or room temp, 25 degrees or room temp. Room temp tends to vary between anywhere from 22 to 25. Standardly, when we say room temp, we generally in the AP problems mean 25 degrees Celsius. Okay. Or 278. Whoa, Kelvin. 298, thank you. 298.15 Kelvin, okay? The standard conversion kind of rate. We know that if G is negative for the overall reaction, we say it is a favorable, okay? Why is this in blue? Why am I doing this to myself? It is a favorable spontaneous process. Okay, we call that, by the way, exergonic. That's like the term, exergonic. We know if it is positive, it is unfavorable, not spontaneous. We call it endergonic. The universe does not like it. Okay, and then if it's equal to 0, there are small children running around like little chickens without their heads off. If it's equal to 0, you know your equilibrium. So, physics review, the first law of thermodynamics is known as the law of conservation of energy. Okay. I don't really feel the need to explain that because I'm assuming you all passed 7th grade and 8th grade and physics. Second law is a little bit maybe newer, although I do assume physics people have heard of this, that entropy of the universe is increased with the spontaneous process. This is where we get the idea that the more entropy, the more favorable that reaction is. So we could call it entropically driven. It's driven by the high entropy, even if it is an endothermic reaction, a positive H, which is unfavorable. If you have more entropy according to the G reaction, the Gibbs-Helmholtz, you could still outweigh the positive enthalpy and take a favorable entropically driven spontaneous reaction. So second law is that entropy increases in universe for favorable or for favorable / spontaneous processes. Who are these wild children running? I mean, I run.
No, but like, who's just running around this?
The third law, this is unique. This is something you want to memorize right here. This is like a one-off MCQ, but it's helpful. Okay. The third law says that entropy of a pure catalyst. Wow, did I say crystal? I meant crystal. Dang. A crystal like a lattice structure, a solid. Okay. at 0 Kelvin, 0 kinetic energy is S equals 0, entropy equals 0, because there's only one microstate. It literally can only exist in one possible configuration. Microstate or configuration. So that's just a table review. Remember that spontaneous does not necessarily mean fast kinetics. You can have a slow spontaneous reaction. We call that a kinetic control reaction or reaction under kinetic control. And it's usually due to high activation energy, super high activation energy, okay? What happens sometimes that you'll see in, you just have to kind of know the existence of these coupled reactions. Sometimes what you see is that we pair a thermodynamically unfavorable, and what I'm going to write is this: we pair a negative G reaction with a positive G reaction to promote the positive G reaction occurring. It's kind of like drag racing. When you get the drift, you go behind the car in front of you and you can pick up their speed. The same idea here. If we can partner one favorable reaction with an unfavorable reaction, we can often create that unfavorable reaction to have a greater favorability as a result. It's just kind of like a boost. Yes. No. It just is kind of picking up the draft wind. Yep. So, but the key is, in order for this to work, you have to share an intermediate. These two reactions that you partner together have to share an intermediate. Okay. So, that way, if your unfavorable reaction is step 1 and your favorable reaction is pulling the product from the unfavorable, Le Chatelier's principle, you drive that reaction forward to fill in the product. You make an unfavorable reaction slightly more favorable because you take a reaction that naturally pulls one of those products. Okay. So that's more of a, I want to take a little BB gun and just kidding. Okay. So it's not. BB guns don't hurt. Another equation for G. This is the new part. Okay. This is where we can find G from the products and reactants. So what if we don't want, and we don't know enthalpy and entropy for the system, but we do have tabularized data for the products and the reactants? We can find the G of reaction by saying it's equal to the sum of the products Gibbs free energy times their molar ratio minus the sum of the reactants Gibbs free energy minus their molar times their molar ratio. Look familiar, right? You've done this with entropy, you've done this with enthalpy. This is just like your summation with tabularized data. This would totally be given in the table. Quick note though, kind of like the enthalpy of a pure element, the G of a pure element is 0. So G formation for pure elements, that includes diatomics and metals at 25 degrees Celsius, because of course we're under standard state conditions and 1 ATM, is 0. So if you're like, they didn't give me what the G is for H2, bro, it's 0. They didn't need to give it to you. Okay. So, okay. Why don't you try these two problems below? One uses Gibbs-Helmholtz, one uses the summation G. So you're going to use two reactions. Two equations for each of these. Oh, actually, both of them just use Gibbs-Helmholtz. Okay, both of them just use Gibbs-Helmholtz, I guess. Oh no, this one uses Gibbs-Helmholtz. And this one uses the summation one. So go ahead and try these really quickly. Okay. So for this problem, what you should have gotten was you should have realized that you had to figure out what was the enthalpy for the process. So you would have calculated H individually and then S individually, and then G individually. So what it would look like is that the change in H for the reaction was equal to products minus reactant. So it would be Cl energy. So what is that? H negative 167.4 plus Na negative 240.12. Okay, that's the products minus the reactants, NaCl solid, H, which is minus 1 minus 4, 11.15. And you would have gotten that the H for this process is 3.87 kilojoules per mole. And then you would have gotten that S following the same process where you do 56 products minus reactants, 56.5 minus 72 not 72, sorry, minus 59. Wow, did I say minus? I definitely meant plus. Minus the reactant 72.13 gives me an overall entropy value for this process at 0.04337 kilojoules per mole. So then my G becomes, G is equal to negative, oh gosh, not negative H, but H minus temperature times change in entropy, which is equal to 3.87 in kilojoules, minus the temperature, well, we're at standard state, so 25, or you'd probably want to put 298 Kelvin, times the enthalpy change, which is 0.04337 kilojoules. And you would get a value for G as negative 9.30 kilojoules per mole for this reaction. So you ended up putting two things together. You put together your overall enthalpy, your overall entropy equations based on products minus reactants, and then you had to put those values into your G Gibbs-Helmholtz equation. Similar thing below. What you would have gotten for your H if you did the same process above is you would have gotten that H equals 84.5 kilojoules per mole. S equals, that looks like a 5. I fully recognize that. I fully recognize. S equals, okay, negative 48.67 joules per mole. Okay. And remember, entropy tends to be in joules, but enthalpy tends to be in kilojoules. So you're going to want to keep track of those conversions in between. And what you would have gotten then is a value for G is equal to change in H minus T, change in S. And I realized I kind of misdirected you thinking that I was rereading something different. Sorry. And I'll just move this up here. Okay. Then what you got? G is equal to, for the reaction, 109 kilojoules per mole. So what you had to do here again is you had to partner that enthalpy products summation minus reactants, entropy products minus reactant summation, and then plug it into the Gibbs-Helmholtz equation. Okay. And you would have had to be careful of those units. The fact that entropy is in joules, but enthalpy is in kilojoules. So whatever you do when you solve and plug into G, you want to make sure you're in the same units of whatever prefix of joules per mole. Okay. So what you would get then is that this reaction, is it thermodynamically favorable or unfavorable for the second sample problem? Thermodynamically favorable or unfavorable for the second? Unfavorable, because it's positive. Because it's got a positive G value. Okay. G. Okay. So this third equation, we have two more equations that go with now equilibrium. We can connect G with equilibrium. So for this one, you could say that the G for a reaction is equal to negative R rate law or not rate law constant, sorry. It's actually the ideal gas law constant times T ln K, capital K. This is capital equilibrium K. You could also, just so you know, K can be represented. Don't forget when you do the K expression, it can be done via molarity, concentration, or pressure. So don't forget when you solve for your K expressions, you can report this based off of molarity or pressure, because remember, K technically has no real units. So as long as the ratio is accurate to being indicative of the relative concentration of each species, then it doesn't really matter. It's the ratio value that you care about, which is your K value. Okay. So what we say then here is that if K is greater than 1, we say that G is going to be negative. If K is equal to 1, G is 0. That means at equilibrium. If K is less than 1, G is positive. So that's unfavorable. The reverse reaction is happening. The forward is not favorable, right? And then the other kind of two, you're like, you don't really need to pay attention to. But this is kind of a nice summary, by the way, of how to connect G and K. You're going to want to know how to connect G and K. This is a common MCQ concept question. Common MCQ concept question where you connect G and K together. Okay. So for this problem below, what we have is R will be given to you on the periodic table in equation sheet. You just got to make sure you choose the R with the correct units. Okay. But it tends to be this R, 8.314. So what you would get is in this problem, you have a given temperature of 250 degrees Celsius. Automatically, you're going to want to convert to the 250 degrees Celsius to Kelvin. So it becomes really 523.15 Kelvin. And then what you have is you simply plug and chug. Like this is really easy. You plug it into your G equation, negative R, 8.314. Okay. Joules per mole Kelvin times T, 523.15 Kelvin times K, ln of K. So natural log of what is my K expression? Well, I was told that my K expression is 24. I literally am just told it's 24. Okay. And so what I find then is I find that my G is going to be equal to a really big number, actually. So I'm going to turn into kilojoules, which is negative 13.8 kilojoules per mole of reaction. So what we would say then it's a negative, it's actually a highly negative G. So this is a very favorable reaction in the forward direction. Because if we're talking about equilibrium, that means the reverse is also possible.
So G just represents
relative favorability.
Okay.
G is just a fancy fake energy concept that we use to categorize reactions as favorable or unfavorable. And it's helpful because it allows us to connect various variables that we might receive. Yes. For standard state. So you could put it in. But actually, this isn't at standard state because what we have is in not at 25 degrees Celsius. So you wouldn't use it for this one because it's not 25 degrees Celsius. Yes. Oh God, sorry. I realized I did not clarify. Alok?
Can you elaborate a little bit on what you mean by relative favorability?
I mean, like, remember you can't really compare Ks. So it's like, well, it's favorable enough to get a positive G.
Okay.
Yeah.
Do you know why exactly G is based on K, given K is based on?
This is a relationship that we've developed to connect G and K. So it's not like truly like one came before the other. It's like we figured out a connection. Mathematically speaking, yes.
Why is this equivalent? Like, why is negative RT ln K equal to the enthalpy minus the temperature times?
It's not. It's not equal necessarily because here, first of all, you have a reversible reaction. So you're working under a completely different paradigm of thinking. That now you're just be thinking about which direction's more favorable, not necessarily an absolute G for one direction.
So those concepts of G are different.
They're slightly different under the contexts. Yes.
And if I did the other thing with this reaction, I would get a different thing.
Well, you should pretty much get similar. Well, actually, that's a really good question. Theoretically, you would get similar, but it means something a little different here.
Okay.
That's what I was. You would technically, if you picked one direction, you should get the same G, but you would get two different G values. This G is saying which direction is more favorable.
Okay.
Okay, so for the last one, I know class is about 10 in 2 minutes. Give me a second. We'll do a warm up tomorrow. This equation, we can also connect it to Q. So we can say that G is equal to change the standard state G for the reaction plus RT ln Q. And that's how we could find at a non-equilibrium status where we're at favorability wise. Okay. And we can walk through these problems tomorrow together for warm up. A lot of it's the same, plug and chug. So we'll do this stuff tomorrow for a warm up because it's all plug and chug. And it's all just various ways to calculate G based off of various variables that you do know. Q, H, S, or what, K. All right, guys, good job.